Okay, so hello everyone, and today I'll be talking about two fundamental data structures in computer science, stack and queue. We already learned about these two terms, stack and queue, in our previous lecture, but we will dive more deep here in this lecture. So, both are fundamental concepts that help in understanding how data is managed, stored, and accessed in a structured way. So, understanding these structures is crucial, especially if you are getting into programming, as they form the basis of many algorithms and help solve real-world computational problems efficiently. Now we already learned about two types of data structures, linear and non-linear. So in linear data structure, we have arrays, queues, and stacks where elements are arranged sequentially, and in non-linear data structures such as trees and graphs where the data elements are not arranged sequentially. Now on these lectures, we will focus on stacks and queues. Both stack and queue provide ways to manage collections of elements, but their access methods differ significantly. Both store and manage a collection of elements. Both are used to solve different type of computational problems. Then here, if you look at the definition, so linear data structures are those where data is arranged in a linear sequence, as I said earlier. Each element is connected to its previous and next element in a single line or a sequence. Now, data items are traversed in a single run, meaning you can go from one element to the next in a straightforward manner. And then the elements are either stored in contiguous memory locations or they can be linked in sequence, which makes accessing and managing them predictable and efficient. So the linear nature allows for easy implementation and helps maintain a consistent order. So array is an example of continuous memory locations. It's stored in a continuous memory location, and stack and queue both are linear but have specific rules for adding or removing elements, which will be discussed in more detail in this next slides. From this point, we will dive deeper into two important linear data structures, stack and queue. So let's just continue. Now, what is stack? So we went through the definition of stack in our last lecture, but we'll also see some example and algorithms of stack here. So stack is a linear data structure that follows the last in first out LIFO principle. This means that the last element that is added to the stack is the first one to be removed. Then we have two key features, push and pop operations. Adding an item to the stack is called push, and removing the item from the top of the stack is called pop. The access to the stack is restricted to one end only, which is known as the top of the stack. So here, if you see the stack of books and stack of plates. Now imagine a stack of books. When you add a book, you place it on top, and when you want to remove a book, you take the one from the top. Same for the plates. So stacks are used in programming for tasks like managing function calls, backtracking, and undo functionality in software applications. So we will now look at some examples how stacks work. Here, if you look at this example, this operation push and pop. Now these are the two primary operations that can be performed on a stack. Push and pop. So push is the operation that adds an element to the top of the stack. And then, so imagine stacking items one on top of the other. When you perform a push, the new item goes directly on top of the previous one. In the diagram on the slide, the push action adds a new item advancing upward. Then pop. This operation removes the element from the top of the stack. It is similar to taking off the top book from a stack. Whatever was placed last will be the first to be removed. Now this diagram shows the pop action removing the last entry added. So the last in first out, LIFO. The stack always maintains a LIFO order. This means the last element pushed is the first one to be popped off. So it is a very important note to remember. So in the diagram, you can see how elements are added on top and removed from the top. The bottom-most element, the first entry, is only accessible after all elements above it have been popped off. So we will see some more example here. Okay, so the push operation is used to add items into the stack, as I said. So initially, if you look at this example, initially elements are A, B, C, which are already in the stack. So so the first one is the initial stack. We already have ABC in the stack. Now the second one, on the second block, we added D. We pushed D. So push D means adds D on top of C. Then we push E, adds E on top of D. And then we will do some pop operation. Now the pop operation is used to delete. So we will first pop removes E from the stack, and then the second pop removes D, making C the topmost element. So the top operation refers to the current location of data in the stack. It is a reference to the last item that was added, allowing us to know which element will be popped off next. So the top moves to reflect the most recently added or removed item. For instance, after pushing E, E becomes the top element. And then after popping E, D becomes the first top element. So this is basically how stack works. Now if you look at here, this is the algorithm for push operation. So if you look at this step by step, the function takes 4 parameters. A top. So first of all, it takes 4 parameter, means it will have 4 variables like A. First it takes A is the stack array. Then top is the current position in the stack. Then item is the element to be inserted, and max, the maximum capacity of the stack. So we have on the first line, we have insertion, A, top, item, max. We have 4 parameters here. Now on the second line, or second step, we'll check for the stack overflow. So we have a condition: if top equal to max, then this checks if the top pointer is equal to max, meaning the stack is already full. Then if it's true, then if the stack is full, it prints that stack overflow and exit. Stack overflow happens when you try to add an element to a full stack. So on third line, it increment the top pointer. If there is space available in the stack, increment the top pointer top equal to top plus 1 to create space for the new element. Now then on fourth step, on fourth line, we have the new item is added to the top position a top equal to item. Then we have then we will exit the item. The function ends after the insertion is completed. So the diagram shows the stack before and after the push operation. Initially, the stack contains elements ABC with C being at the top. Then after pushing D, adds the new element D on top of C. So it is important to understand that a stack has limited capacity. If you try to push an item when the stack is full, it results in an overflow error. So now we'll see a pop algorithm in next slide here. So if you see on the first step, like the push one, we also have here we have 3 parameters for deletion. So the function takes 3 parameters: a, the stack array; top, the current position of the stack; and item, the variable that will store the popped value. Then on second line, we check for stack underflow. So if top equal to 0, then this checks if the top pointer is 0, which means the stack is empty. We cannot take out anything. So if the stack is empty, print stack underflow and exit. Stack underflow occurs when you attempt to remove an element from an empty stack. Then on third step, we assign the top element to item. The value at the top of the stack is assigned to item. So item equal to a top. This stores the value of the top element for any subsequent operations. Then on fourth step, it decrement the top pointer. The top pointer is decremented top equal to top minus 1, effectively removing the top element from the stack. Then it exit the function after the function ends the removal process. So the diagram shows how the stack evolves as multiple pop operations are performed. Now initially we have the stack elements with 5, 10, 12, 15 being at the top. 15 is at the top. Then after the first pop, it removes 15. Then the new top is 12. Second pop removes 12 and the new top is 10. This continues until the stack is empty after the final pop of 5. So you have to remember the stack overflow and underflow both, because these are the errors we often get on stack. Okay, so here is another algorithm to display in stack. So the function display top, we have top, I and AI, which have the parameters top, which indicating the current position of the stack, I for iteration, and AI, that stack array elements. On step 2, it check for stack empty. So the condition checks if top equal to 0, then this checks if the top is 0, which means the stack is empty. If the stack is empty, it prints stack empty and exit. This indicates that there are no elements to display. Then on third step, it iterates from top to bottom. So for I equal to top to 0, the loop starts from the top of the stack and goes down to the bottom, I equal to 0. Print operation, where the command print AI outputs each element of the stack. Then the function ends once all elements have been printed and exit the function. So the diagram shows an example of example stack where the word reverse is stored. So with the letter E at the top, the display algorithm will print the stack element starting from E topmost to R bottommost. So the key concept here is traversal order. The display operation shows the elements starting from top which means the most recently added element is displayed first. This is useful for understanding the current state of the stack, especially when debugging or reviewing data stored temporarily. So we'll also see some more real life examples of stacks on our next slides. So here in this slide we'll focus on reversing string. This is a common and simple application of stacks, which is to reverse the characters in a string. So how it works? The reverse is to reverse a string. The characters of the string are pushed onto the stack one by one as it is read from left to right. Once all the characters are pushed onto the stack, they are then popped out one by one. Since a stack works on a last in first out principle, the last character that was pushed onto the stack is the first one to be popped. This results in the characters being retrieved in the reverse order, effectively reversing the string. For example, if you consider the string hello, step 1, each character's HELLO is pushed onto the stack. Then on step 2, as we start popping the elements of the stack, they come out in the order OLLEH, opposite, like reverse, in reverse. So which reverses the original string. So the process of pushing and then popping helps in reversing the order of elements. This is a direct consequence of the LIFO behavior of stacks, making them very suitable for reversing operations. So reversing strings is often required in data processing tasks, text manipulation, and even when dealing with specific algorithms that involve backtracking or evaluating mathematical expressions. So here we'll see step-by-step explanation of a reverse example string. So first we'll read the string. The string reverse is read from left to right. Step 2, pushing characters onto the stack. As each character is read, it is pushed onto the stack. This means R is pushed first, followed by E, V, E, R, S, and then finally E at the top. Now the diagram on the slide shows how each character is pushed onto the stack. So after pushing all characters, the stack contains the letters of reverse in the order they were pushed, with the last character E being at the top. Now when you will pop this reverse string, to reverse the string, the characters are popped from the stack. Since it operates like LIFO, we will pop out ESREVER. It will come out like that. So the stack's LIFO property makes it a perfect data structure for reversing the order of elements, like such as characters in a string. So this example clearly demonstrates how a stack can be used in practical text manipulation tasks. So reversing strings is a fundamental task in many text-based algorithms, such as parsing data, reversing words in a sentence, or even validating palindromes. So now we'll see an application of stacks, which is validating expressions with parentheses. Now so stacks are also used to verify whether an arithmetic or logical expression with nested parentheses or other similar symbols like braces and brackets, which is properly balanced. So the stack helps ensure that for every opening parenthesis, brace or bracket, there is a corresponding closing symbol. The symbols should also be correctly nested, meaning that parentheses open most recently should be closed first, according to the LIFO principle. So how the algorithm works? As as the expression is scanned from left to right, every time an opening parenthesis or symbol like the bracket, excuse me, so the bracket, parenthesis, or curly braces, so every time an opening parenthesis or symbol is encountered, it is pushed onto the stack. So this is the first step. Now on second step, when a closing parenthesis or symbol when a closing parenthesis or symbol is found, the stack is popped. Now on step 3, the program checks whether the popped symbol matches the corresponding opening symbol. If not, the expression is invalid. On step 4, if after processing the entire expression the stack is empty, the parentheses are balanced and valid. If the stack is not empty, it means some opening symbols were not properly closed. So if we consider an expression like we are starting with two parentheses and then a plus b, and then we're closing one parenthesis, then star, then another parenthesis c minus d, and then closing both the first one and the third one. The algorithm will push the two opening parentheses onto the stack and pop them when their corresponding closing parentheses are encountered. So since the stack is empty at the end of the process, the expression is valid. Now the LIFO nature of the stack ensures that the most recently opened parenthesis is the first one to be closed, making it an ideal tool for validating nested structures. So this technique is commonly used in compilers and interpreters to validate the syntax of code, ensuring that all expressions have balanced parentheses, brackets, and braces. So here is an example. You can see here. Now this is an example of valid or invalid input parentheses. Like okay, so invalid inputs, the left side of the slide shows these valid inputs and the right side is invalid inputs. So here this we have braces inside the under the valid inputs. We have braces in first line. This is a simple valid input where the opening brace is properly closed with the closing brace. So next we have parentheses. Like this example has nested braces and brackets, and each opening symbol has a corresponding closing symbol in the correct order. So if you look at the middle one, the center one, which is the inner braces or inner brackets, so inner bracket close first, then the second one, and the last one means the first one. So that's how stack works here to have the correct order. Now on the third one, on the third one, if you look at the third one, even in more complex nesting, as long as the symbols are opened and closed correctly, the input is valid. Okay, so if we look at the right side, invalid inputs, where we have curly braces and then a parenthesis, but it is not closed. The parenthesis is not closed. Um, so um, so we do not have a closed parenthesis, and which makes is it invalid. Now the second one, if you look at the second one, that is also invalid, and the third one and the fourth one. So basically this is just to show you the examples of how invalid inputs looks like and valid inputs are. So now we'll move on to queue. So a queue is a data structure that operates on the first in first out FIFO principle. The analogy used here compares a queue to a line of people waiting for a bank teller. The first person to join the line is the first to be served, which mirrors how elements in a queue are processed. Now we have front and rear, two parts of a queue. The front of the queue is where elements are removed, like dequeued, and the rear of the queue is where new elements are added, inqueued. In the diagram, people are lined up in the queue and the rear and front are clearly marked. This is where the first person or element will be removed from the queue, and on the rear where new people or elements enter the queue. Now the queue behaves like a real-world waiting line where individuals are processed in the order they arrive. This analogy helps to easily understand how queues work in data processing and system design. Now we could have some applications of queues like task scheduling, printer queue, customer service. These are the example. So if you look at the next slide, here we are doing the in-queue and we're doing the in-queue operation. So in-queue is the process of adding an element to the rear of the queue, as I said earlier. In the diagram, a new person or element is entering the queue at the rear, which is where all new additions happen. The C++ queue class may refer to this as a push operation, but it is commonly called in-queue across most programming languages and contexts. Now, how in-queue works? A new element can only be added to the rear of the queue. Once added, the element must wait its turn to be processed, as elements at the front are processed first. Now the queue grows from the rear as new elements are added, while elements leave from the front when processed. So think of a queue as a line of people, like I just said, where new person is adding the queue and then getting out from the front. So the person highlighted here in this diagram is in-queued, like joining at the rear, which pushes the other elements forward in the waiting line. So the in-queue operation is vital in managing systems that require ordered processing, such as job scheduling or buffering data in systems where tasks must be handled in a strict first-come, first-served manner. Now here, this is the operation of dequeue. So dequeue refers to the removal of the element from front. In the illustration, the highlighted individual is being removed from the front of the queue, which is where elements are dequeued for processed. The C++ queue class may refer to this as a pop operation, but in most contexts it is referred to as dequeue. Then, so once removed, the next element in line becomes the new front, of the queue, maintaining the FIFO order. So here the dequeue operation is critical in ensuring that tasks or elements are processed in correct order. Like I just said, like for task management, job scheduling, these things same, because the whole process is a one process, like removing elements and adding elements, and doing the whole operation is a one operation. Okay, so the queue class, C++ queue class. So the C++ standard template library, like STL, includes a queue template class that allows for the implementation of queues in program. This class is designed to manage queues of any data type using templates. Now the template parameter in the queue class is the type of the item, a type of the items that can be added to the queue. The use of a template makes the queue versatile, as it can store any data type such as integers, floats, objects, or user-defined data structures. So we already learned about templates, and we already went through we already did the revision for C++ codes in our lectures, previous lectures. Like first 2-3 lectures were about the C++ codes, so you already know about template. So when we use a template, we can have the option to make the function versatile, so we can use anything like integers, float, objects, or anything using the same template, if you remember. So if you could just call the queue class inside the template, then if we have a constructor queue, let's say we can have a constructor to create new queue. Then we can have push, where we can add an item to the rear of the queue, and then pop, which removes the front item from the queue. Then we can have an empty function which checks whether the queue is empty. And then another one could be front. This function returns the item at the front of the queue without removing it. Now, using those terms and functions inside a template using the class queue, we can just make it work. So there are many benefits of using a queue template class. First of all, reusability. We can just use it as many times as possible, since the class is templated. So we can just use it with different types of data without rewriting the code. Now next, so the queue template abstracts the internal workings of the queue, allowing the programmer to focus on higher level logic rather than queue implementation details. So you have already built in a queue function, so that we don't have to implement a queue function again. You can focus on higher level logics rather than just implementing a queue function. So so that's how we can use the queue class, and we'll see an example here. So a queue can be implemented with an array as shown here. For example, this queue contains the integers 4 at the front, 8 and 6 at the rear. So just like our stack implementation in the previous lectures, one way to implement a queue is to store the elements in an array. So an array of integers to implement a queue of integers. So we have 4, 8, 6 on the addresses 0, 1, 2, and then for the addresses 3, 4, 5 we don't have anything. So here if you now so the easiest implementation also keeps track of 3 numbers. The size could be as small as 0 or as large as the number of items in the array. The index of the front element is stored in the first member variable. The front item in the queue is at that index of the array. The next item is after the first one, and so on until the rear of the queue that occurs at the index stored in a member variable called last. So if you look at here, we have 3, 0 and 2, 3 numbers. 3 is so 3 is size, then first, then last. Now here if you look at this one, when an element leaves the queue, size is decremented and first changes the first changes too. So if you look at the size here, on the previous slide we had the size 3 because we had 3 elements, and then we have the first one was 0 there because the first one here was the address of the first value was 0. That's why we had a 0 on the previous slide, but now the first is 1 because we removed an element, so the size decremented. So the first is now 1, the address is now 1, and the last is still 2. This shows how the member variables change when an item leaves the queue. So if you look at here, when we will add an element and the size will increment and the last will change here. Now the size is 3 again and the first is still 1, but when we added 2, the last is now 3. Previously the last was 2, now the last is 3, the address. And this shows how the member variables change when a new item enters the queue. For a fixed size array, a new item may enter only if the current size of the queue is less than the size of the array. For a dynamic array, we could increase the size of the array when the queue grows beyond the current array size. Okay, so now at the end of the array, we'll see here there's a special behavior at the end of the array. For example, suppose we want to add a new element to this queue where the last index is 5. So here an array implementation of a queue must have special behavior when the rear of the queue reaches the end of the array. In this example, suppose we want to add the number to the queue, we can do so, but it will come by putting it at the location 0. So it will reverse if that location is not already used, but if it's used already, we can just go to 1, and if 1 is also already used, then we can go to 2. So at the end of the array, the new element goes at the front of the array if that spot isn't already used. Now the size of the array is 4 now because we have 4 elements here, and the first is still 3. First is not 0. If you carefully see here, the first still remain to 3, but the last change to 0 because we added the element 4 at the last and it went to 0 because the array is we had the last element in the address 5 before, but when we added, it added on 0. If it's so it was empty, that's why it added to 0. So the now the last element is 0. Now, so here are some of the key aspects of an array implementation of a queue. First of all, it is very easy to implement. but it has a limited capacity with a fixed array, or you must use a dynamic array for an unbounded capacity. Special behavior is needed when the rear reaches at the end of the array. Then it will flip or reverse to front and start from front again. Okay, now we'll see linked list implementation. Now a queue can also be implemented with a linked list with both a head and a tail pointer. So we saw the implementation of an array, queue implementation of an array, and now we will see a queue implementation of a linked list. So as I said, it can also be used to implement a queue, but we must maintain both a head and a tail pointer because we need access to both the front and the rear of the queue. So if you look at this linked list, the one node is pointing to the next node. So we'll see the implementation here. Now here, which end do you think is front of the queue and why? So here, does it matter which end of a single linked list we use for the front of the queue? Of course, we could put the front of the queue at the end of the linked list, but it would be hard to remove an item. Do you see why? The head PTR points to the front of the list here because it is harder to remove items from the tail of the list. So, like stacks, queues have many applications. Items enter a queue at the rear and leave a queue at the front. Queues can be implemented using an array or using a linked list. Now we will also learn more about linked list in detail in our future lectures which is coming in next week's like following weeks. So next week we will have midterm exam. So I will make an announcement about the details and the everything, the timing and the question types, everything. So make sure you read the announcement and email me if you have any question about midterm. And so because we will learn more in details about linked list later on, so that's why I just went through here in this slide. I just went very short. So that's all for today's lecture. Let me know if you have any question. Thank you.